webinar. My name is Kristen Corcor. I'm one of the Inside Sales and Business Development Coordinators for ALS Oils and Lubricants North America. We're excited to have you join us for this informative session on generator maintenance essentials. We have a lot of valuable content to cover, and we're fortunate to have Gary as our expert to share the insight and knowledge he has gained over a career that spans several decades and continents. Gary is currently the Technical Director for ALS Oils and Lubricants in North America, based out of Cleveland, Ohio. Before we dive in, I'd like to remind you that we will be holding a Q&A session at the end of the webinar. As we go through the presentation, feel free to submit your questions via the chat feature, and we'll address as many of them as possible during the Q&A. Now let's get started. Gary, I'll turn things over to you.
Thank you, Kristen. Hi, everybody. Good day. This is going to be a fairly full session to go through, so I may go through some of the slides fairly quickly. As Kristen says, if you have any questions, please post them. We'll attempt to answer the questions at the end of the session, and anything we can't get to, we'll reach out and directly answer if we can. All right, so today's webinar is all about standby generator maintenance. And we're going to be looking into why you do this and what we can get out of the process. So the slide I have on screen now is just covering the bullet points of what we're going to go through. We are going to talk about your maintenance strategy. We're going to talk about the importance of maintaining generators. And the real key thing that we're going to start to look at is these three things here, which is, if you test the engine lubricant, what information can you get? When you're testing your engine coolant, what information you can get? And then your diesel fuel, what information can you get from testing diesel fuel? And we will look at each one of these in this presentation and discuss what information you can expect to receive from analyzing these fluids from your standby generator. And then by monitoring these things, we can expect a couple of benefits. We can extend the life of the equipment, we can increase the reliability, and we can lower cost of operation. But in reality, it's the center point that is the critical one for us when it comes to standby generators. Standby generators are very much like an insurance policy. We wish we didn't need them, but reality is we do, and we really need to count on them when we need them. And a standby generator is one of those things that failure is not an option. When you need to run that engine needs to be able to produce power for you to tide you over until prime power can come back. So our real goal, the thing that we are most trying to do with maintaining a standby generator, is to ensure the reliability of that engine. We want to make sure that the day we need that thing, it will work and it will do the job we need it to do. Looking at maintenance strategy, these can be broken into four main categories, or generally are broken into four main categories. And these tend to show an evolution in thinking and as how we maintain equipment over time. Starting at the left, reactive maintenance, or better known as breakdown maintenance, is a strategy where basically you don't do anything. What you do is you wait until something stops working, and when it stops working, you go and fix it. Now, most people say, well, this is not a really good way of looking after a piece of equipment, but reality is it can be. Probably a good example of this is light bulbs in office buildings. We don't go around checking to see if the light bulb is going to fail tomorrow. What we do is we just wait until it stops working, and then we go and get a new one out the cupboard and we install it. And so that's just how we will maintain that piece of equipment. So if we have something that is easy to change, you can keep it on hand, it has a low impact on safety or production, breakdown maintenance can be a viable way of running that piece of equipment. But standby generators generally don't fall into that category. We don't keep lots of them on hand to just use, and if one doesn't work, we just grab another one. The next evolution was to move to what is now generally referred to as preventative maintenance, but this is essentially a time-based maintenance practice. So what we will do is we will say, okay, that engine over there, every 90 days, we're going to go and change the oil in it. And we'll set up a calendar and we will do this oil change every 90 days. This has a good role to play within maintenance strategies. What you need to do is establish what is the typical time interval for a particular event to occur, and then you work out, all right, this tends to happen at 100 days, the oil dies, so we're going to change the oil at 90 days, and that's how this is developed and works. The problem, though, is that something like a standby generator can have a very variable work cycle. So an oil that is fine in 90 days in one work cycle may not be fine in another work cycle, just simply because the number of hours the engine runs in that cycle can change. So that moves on to the next sort of level of maintenance that is done, and that's now referred to as predictive maintenance. So when people talk about predictive maintenance, what they're really talking about is this thing here, condition monitoring. And what we do, instead of just using a calendar to decide when we're going to do things, is we start monitoring the condition of the thing of concern. So in this particular case, it's the engine oil. So instead of just changing it every 90 days, what we will do is we'll start testing this oil and establish its condition. And then we will see that maybe after 40 days, it's full of water, we need to change it. That then becomes an action that's taken before our calendar event. Or at 90 days, we can look at it and say, there's nothing wrong with this oil. We can run it for another 90 days. And that is the process of condition monitoring. And there's various things that you can monitor the condition of, and methods of looking at things to try and determine, when do I really need to take action? And so we move away from a time-based strategy to an on-condition-based strategy. The third or fourth level of maintenance is proactive maintenance. This is basically a technique where what you do is, when you learn of a particular problem occurring on one piece of equipment, you apply that learning to other pieces of equipment. So one of your generators develops fault at a particular hours. You can now go, do I have any other engines that are in a similar state at similar hours? And you can now go proactively start investigating and working on those engines. And so that's tend to be referred to as proactive maintenance. Reality for standby generators, the center two are where most people would be operating. We will have a schedule of events that we do on a time-based strategy, and we will also have condition monitoring, where we'll be monitoring various things, and depending on the outcome of that monitoring, we will decide when to take action. The reasons we do this, reduce maintenance costs. Well, effectively, what we're trying to do is reduce breakdown costs and lost production costs. We want assurance that the maintenance is working, and that's probably the most critical thing for us from a standby generator point of view, is that it's this reliability factor. We want to make sure that when we need this engine, it will work for us. So stop the compound effect of mechanical failure. What that's referring to is that many failures start from something small. So something small goes wrong, and then as it fails, you get a cascading effect of various things that are failed in subsequence to or because of the initial failure. So you may have a bearing that begins to fail. Initially, the cost of repair is just simply the cost of replacing a bearing. But if that bearing is allowed to fail, it will then damage a crankshaft, and then it'll damage the block. And so the cost of repair grows rapidly as the failure progresses. So we really want to stop things at a very early stage when a failure develops. Reduce waste. So if you don't need to change the oil, keep it in service, you reduce the cost of purchasing the lubricant in the first place. You also reduce the cost of the disposal of that and the environmental impacts that disposal may have. And quickly address failures and downtimes. It's really enabling you to plan these things. The problem with breakdown maintenance is that the failure happens when the failure wants to happen. As soon as you move into condition-based and proactive-based style maintenance practices, you can start to plan when you want to do something and say, we've got a developing problem here. We are going to schedule next Wednesday at this time to do this job. So you're now starting to plan when events are going to happen instead of just waiting for them to be imposed on you. Consequences of failure. Obviously, your standby generator, as I said, is an insurance policy. When your prime power goes down, you still have power because it's going to be provided by your standby generator. If that fails, then there can be serious consequences to it. And so there's two we've got on screen. One involves COVID vaccines, where a storage facility lost prime power, but the standby generator failed shortly after coming online. And so we now had a lot of vaccines at risk. And if you remember back in those days, there was a lot of drama around this. So that would have had a serious consequences for that particular facility. And we've got another story here about a fire that was running through. They lost prime power because of the fire itself, but the standby generators also failed, which meant that they didn't have water pressure, which meant it became very difficult to fight these fires. So these are some of the consequences. I personally know of a case where a standby generator for a plant that was basically producing plastic material from oil. The standby generator failed about 30 seconds after taking load from a loss of prime power. That sudden loss of power totally to the plant meant that we had an uncontrolled gas leak, which resulted in the evacuation of a town. And these are the type of things that can be consequences of it. So obviously it's very dependent on the nature of what you're doing and what this generator is going to be used for, but there can be serious consequences to losing your standby generator when you really need it. Regulations, because standby generators are so important, there are federal, state, and even city ordinances that can govern how they need to be looked after and how they need to be categorized, etc. I'm no expert on this, but it just sort of the one that I know that gets spoken about the most is the National Fire Protection Association, the 110 code. It just basically details how you tell what type of generator you have, how it's classified, and how it should be looked after and operated based on that classifications. From there, you need to start looking at the federal, state, or city ordinances that may apply to that particular generator. But it is something to be aware of, that there can be things that have to be done from a regulation point of view. And some of the testing that we do for generators is purely to meet and comply with those requirements. We do have a test pack that is specific for generators that will include the three main fluids that we're going to analyze, so the oil and the cool and the fuel, and those are available from the laboratories themselves. So what are we trying to do? Essentially, we're trying to look at three things, and we're looking at these three things on the three fluids. So it could almost be a story of threes here today. But we want to look at the machine wear behavior. So we tend to look at what kind of metals are being found in these fluids. We look at the contamination, what sort of contamination we are finding in these fluids and what that impact will be on the fluid itself. And then we're also looking at the health of the fluid. Is the fluid still in good condition, or is it degrading? All right, so starting with lubricant analysis, so the analysis of the oil from the engine. We again have three things that we are going to be looking at, and we are going to be looking at our wear levels, we're going to be looking at contamination, and we're going to be looking at contamination. So this is what you can expect to find on your report. You can expect to find a section of the report telling you what's the wear behavior. You'll find a section of the report that'll be talking about contamination, and is there contamination in this oil, and will that impact the life or the machine itself? And then lastly, we'll be looking at the lubricant condition. So when it comes to wear metals, something to be aware of is that most standby generators do not run very much. They tend to run for short periods just for testing purposes. And as a consequence, wear is not such a big factor. These engines generally do not wear out, but corrosion is a factor. So when these things stand for long periods of time, corrosion can occur. And corrosion tends to involve the same metals that are found in wear levels. So the wear metals that we're looking for normal wear generation in a normal engine that's running 24/7 can also be the indicators of corrosion within a standby engine. So while we refer to these as wear metals, we're really looking at corrosion metals when we're coming to standby generators. Just to run through the metals that we're talking about when it comes to wear and corrosion, iron is a big one. It's a primary indicator of all sorts of processes. What we'll tend to find is that your engine will often have a cast iron cylinder block. it may have cast iron cylinder heads. If we're seeing corrosion, these are the two things that are most likely to corrode. This is most likely to be where iron is coming from if it is starting to increase in your engine. If it's coming from a wear process, it can be your liner, and that will generally be also showing evidence of ring and other wear taking place. It can be coming from the crankshaft. It can be coming from timing gears. These tend to be the sources of iron in an engine from a wear process or a corrosion process. But as I say, the corrosion normally involves the block in the head. Aluminium is a very popular metal in engineering just simply because it's lightweight and it's easy machining ability. So again, it is and can be corroded in service. So if we start to see increases in aluminium, this is the kind of thing we've got to look for. Do we have an aluminium cylinder head? That will be a source of corrosion. Do we have auxiliary equipment like fuel pumps and casings? A lot of casings are made of aluminium, and if some sort of wear is taking place, it can start to rub against the casing and produce metal from the casing itself, or we could just get corrosion where the aluminium is corroding into the solution. Copper is commonly used bushing, thrust washers, that type of thing. Something to note about copper is that copper is very seldom used in its pure form. In fact, it's almost certainly never used in its pure form. Pure copper is very brittle, and it doesn't make a very good wear material. It's why we had the Bronze Age and not the Copper Age back in history. And the metal that is most commonly alloyed with is tin. So if we see an increase in copper and we see an increase in tin, that is something to be concerned about. And that will almost invariably mean that we've got a busher or a thrust washer that's taking strain. And that's generally not a good thing. We need to figure out what it is, and we need to be able to take action to fix that, because if it's allowed to carry on, it can result in total failure of the machine. Lead is normally used as a soft material on plain bearings. So our big end bearings and our small end bearings generally have a surface layer that is 80 to 90% lead based. Lead is soluble in acid solutions. So if acid is accumulating in the oil, it can also be come from corrosive sources. So even though the engine isn't running very much, if we start to see increases in lead, that would suggest that our oil is becoming corrosive and is starting to dissolve the bearings, and we need to stop that. Chrome is a metal that's used for hardening steels, and similar with nickel. Nickel is also another metal that's used for hardening steels. If we see increases in chrome, piston rings are normally your main source of where it's coming from. So if we get an increase in chrome, we get an increase in iron, and we get an increase in aluminium, that's the piston skirt, we know that we're looking at a cylinder pack wear situation. So that at least helps us identify where the wear is taking place in the engine. Nickel, as opposed to chrome, is often used in roller bearings, ball race bearings, those type of things. So if we see an increase in iron and an increase in nickel, that's the kind of thing we've got to be worried about. Is there a bearing that's failing? And generally, these bearings don't produce wear metal. If they're producing wear metal, they're failing, and that's not a good thing. Titanium, vanadium, hardly ever will show up in a standby generator. These are more metals that are used in things like gas turbines and that type of stuff. So if you're running a gas turbine generator, it may be a problem. And obviously, if it appears in the oil, that's quite a serious problem, because it should not be showing up there. Dirt, airborne dust is abrasive to your piston ring and liner area. And so increase in piston ring and liner, increase in dirt, it means dirt is being sucked into the induction system and is causing wear. Water can come from direct sources or from coolant entry. So we kind of separated them into two categories. If we've got water in the oil and there's no indication that it's coolant, then we're probably looking at condensation, rainwater, or washdown water. Somebody's got over-enthusiastic with a pressure washer. If that is found to be the source, we need to identify it and stop it, and we need to change the oil to get that water out of there. Water will promote corrosion, and so we really don't want to have water in the oil. If it's coming from coolant, then obviously means that the coolant is leaking into the oil somehow, and we need to identify and fix that. And the main way we can tell it's coolant as opposed to fresh water is by looking at the sodium result and the potassium result. Sodium tends to be your additive in the older style coolants, and potassium tends to be the additive they use in the modern long lifestyle coolants. So depending which particular coolant you have in use, it could depend which of these become the dominant value, but invariably both of them will show up. Diesel fuel, if fuel is getting into the oil, it's going to thin the oil down, lower the viscosity. That in turn can eventually cause wear. So we want to deal with that problem if it comes up. Similar with fuel soot, a small amount of soot is not a problem, but if it accumulates and we get too much in there, it can start to cause deposits to form, and it can break rings and things like that. So we need to deal with that problem if it occurs. Nitration, sulfation are byproducts of combustion, and these are both acids. The nitration is due to nitrogen in the air. Sulfation is due to sulfur in oil that's on the line of wall, that type of thing. If these acids build up, they will begin to attack your softer metals like lead and copper. So you will see them going up in the oil. You will see these values rising. The best thing to do in this scenario is to change the oil to flush this out and to try and get a fresh oil in there that does not contain acids. Standby generators do have a problem with low operating temperatures. If the engine has been run on a regular basis but without load, it may not develop enough heat. And if it doesn't develop enough heat, these acids tend to condense into the crankcase and become more problematic than they would on an ordinary engine. So there are something to watch on standby generators. Viscosity is a primary indicator of the condition of the oil. It should remain unchanged. It should be fairly stable. Normally what happens when you use a new oil in an engine, the viscosity drops a little bit from a mechanical shearing action as the engine starts to run, and then it should just stabilize and remain unchanged. If it goes up, that means the oil is degrading due to heat. If it goes down, it means it's contaminated with something like diesel fuel or something else is getting in there that shouldn't be there. Additive levels also should remain stable. If you suddenly see a shift in the additive levels, that's indicative of somebody's topped off with the wrong stuff. Or if this engine has a power pump or something like that, it may be a hydraulic oil is transferring into the engine. The things to look for are these top three elements, calcium, phosphorus, and zinc. They should remain relatively stable sample to sample. If they move, it means something is changing within the oil. Oxidation is an indicator of thermal degradation. So if we see oxidation going up, you'll also tend to see viscosity going up. That just means the oil is getting too hot, and that's what's killing the oil. This generally is not a problem with standby generators, because generally the problem is these engines tend to run not hot enough until they're really needed and running under load. Monitoring the coolant. Again, we look at three different things in the coolant. We look at corrosion, we look for contamination of the coolant, and we look for degradation of the coolant. Corrosion is a big concern. We want the coolant, and a lot of the additives that are in coolant are just trying to inhibit corrosion from taking place. But if we start to see an increase in things like iron, aluminum, copper, that will tell us that corrosion is occurring in our coolant. And the best course of action is to change the coolant when this happens. Because if we allow this corrosion to happen unchecked, it will weaken and damage the engine. Things that contaminate coolant. The most common contaminant you'll find in coolants is tap water. People filling off the radiator, just taking water from a drinking tap. The problem with tap water is that they contain salts, and we have to have these salts because without them, the water is not very good for us. In fact, the water that you want to use in a cooling system to top it off needs to be pure. It needs to be pure water, and drinking pure water actually is bad for you because we need the salts. So essentially, if you can drink the water, don't put it in a cooling system. If you can't drink the water, you can put it in the cooling system. The way we identify if this is happening is by measuring what's known as the electrical conductance of the fluid, and this is normally reported as a value called total dissolved solids, or TDS. If this number increases dramatically, so let's say the number is running in the hundreds and it jumps to the thousands, that's normally an indication that somebody has put dirty water into the system and we need to flush it. Petroleum layer, if any hydrocarbons, engine oil, fuel, that type of thing is getting into the coolant, and both of those can get into the coolant, it tends to form a layer on the surface of the coolant, and this is not a good thing. It normally is indicative of some sort of mechanical problem developed that's allowing the oil to transfer into the coolant, and sometimes it goes the other way as well. We'll start to see coolant in the oil. We need to figure out what that is and fix it. Solid material, this is a visual observation done on the coolant, and the things that we are most looking for are red oxide rust, black oxide, which is a form of rust that occurs at very high temperatures. So if we have got a section of coolant that's not flowing in an engine, we've got a low flow zone in the engine, it will tend to produce black oxides. We can get debris, this is normally just somebody using dirty containers to put water into the system, that type of thing. Rubber particulates, if a hose is starting to degrade on you, it will leave behind little black bits of the hose, and we tend to find that in the coolant. And obviously that's not a good thing. When we see this, we need to figure out which hose is failing and replace it before it fails completely. Coolant is made up of water, glycol, and inhibitors. And what tends to degrade is the glycol and the inhibitors. So glycol will degrade due to heat, and once we get up above 80 Celsius, degradation of glycol can begin to occur. It's a complex process that it goes through as it degrades. I won't bore you with all the chemistry that happens because there's multiple steps in this degradation. But what is important to know is that one of the products that is formed when glycol is breaking down is ammonia. If you get a strong ammonia smell coming from a coolant, you don't need a lab, you know you have a problem. That will tell you that the glycol has been broken down, and that would suggest that this coolant is getting excessively hot, which we need to investigate why that is happening. The inhibitors, their process of degradation is complex and depends on the type of inhibitors, but effectively what happens is the inhibitors disappear over time or break down. Excuse me. Give me a second. And when that happens, normally the only thing you can do is to replace the coolant. If this is happening rapidly, it means something is stressing the coolant, and that something is normally high temperatures. So again, we need to check, why is the system running so hot? Fuel, again, we tend to look at three things on the fuel. We're looking at the fuel quality, we're looking at the fuel contamination, and we're looking for fuel stability. Now, this last point is something that's really important for standby generators, because a standby generator needs to have enough fuel to run for however long it's expected to carry power for. So you may have quite large storage tanks just to make sure you've got enough, fuel to run for 48 hours or whatever it might be to keep the power up before prime power can be brought back. And that fuel could be in storage for many years. And so we need to make sure that this fuel is still in good condition to use in the engine. The tests that we run through, there's actually quite a lot of tests we can run through. I'm just going to go on the most important ones. And to me, one of the very important ones is the distillation range. The distillation range is just the temperature at which various things happen to the fuel when we heat it up. Initial boil point is, as it says, the temperature at which it starts to boil. The 10% is telling us how hot we had to make the fuel to boil 10% off. 50%, how hot did we have to heat the fuel to get rid of 50%? 90%, how hot do we have to make this to get rid of 90% of the fuel? How do we boil, how much temperature is needed to boil off 90% of the fuel? And then the temperature at which boiling stops. Now, for these first two values, your initial boil point and your 10%, if those numbers change, if they increase, so if the temperatures go up, it's going to make starting harder. It means that this engine is less likely to start when you need it. And this normally happens if the fuel ages and is, slowly oxidizing. It tends to do this. If the end temperature, so your 90% in particular, starts to increase, that will start to influence combustion. And you may reach a point where the engine is unable to burn this fuel efficiently. and we start to get soot, black smoke, that kind of thing being generated from the engine, and those then cause problems for the engine. So essentially what you want is these temperatures need to stay much the same. You don't want them to be increasing or decreasing. If they're decreasing, it means the fuel has been contaminated with something like gasoline, and that again is also a bad thing. Flashpoint, that just helps us know at what temperature the fuel will ignite. In some instances, you need this information for safety purposes. So they need to know, okay, we've got to have a fuel that meets a certain flash point, otherwise it's hazardous in the environment we're in. So it helps us with that. It will also help identify if something like gasoline is present. Fuel cleanliness is important. If the fuel is dirty, it tends to cause two problems. One is filter plugging. So the filters need to be replaced more frequently, and obviously the engine loses power when the filter starts to plug up on it. Also, if any of that particulates are getting through to the injectors, they tend to be very damaging to the injectors. So we want to try and keep the fuel as clean as possible. And the general accepted level is 18, 16, 13. And what I mean by that, it's a code number that is used to represent the number of particles in three ranges. So we have got 4 micron, 6 micron, 14 micron are the ranges that are used. And there's a long history that I don't have time to go into as to why those numbers are. But essentially what we'll find is that in our 4 micron count, we will find we've got a lot of particles, and then it gets less, and then it gets even less as the particles get bigger. Diesel is not good at carrying particles. As they get bigger, they fall out. So you do see this rapid drop in the count as the sizes go up. But essentially, if we look at 4 micron and we've got 3,750, and we will see that falls in our table between 2,500 and 5,000. And so it's assigned a value of 19 for the 4 micron. It's then assigned a 16 for the 6 micron. And then it's a 14 for the 14 micron. And that's where this 19, 16, 14 number, which if you remember the previous slide, this would already be considered too dirty for a typical fuel. So if you get a count like this, our fuel needs to be cleaned up. We'll need to run additional filtration to try and remove these particles. The thing to know about this table is that as each number increases, we are doubling the number of particles. So if we go from, let's say we want an 18 as our first number as our limit, and it suddenly jumps to a 20, that means we have trebled the amount of particles that are present. We have really increased the number of particles, even though it's only a 2-number increase. That actually represents, it's logarithmic, the scale. It represents a dramatic increase in the number of particles. Cold filter cloud point, that tells us the temperature at which the fuel is going to begin to drop wax and block filters. The cold filter plugging point is the actual point at which the filter will block from wax. There's also a thing called a pour point, which also is a similar bit of information. All of this relates to winter. How cold can this fuel get and still function within our system? And we also do a bacteria test. This is a positive growth test. In other words, we look to see, is there bacteria that is viable and will grow in your fuel? If any does begin to grow, we will let you know, excuse me, how much grew. And obviously any growth of bacteria is a bad thing. It will need to be dealt with. We want to keep our fuel dry, so we want to aim for a level of 200 ppm or lower for our water content. If we keep the fuel clean, cool, and dry, it generally lasts a long time. If the water content goes up, bacteria growth becomes almost a guaranteed problem. Also, corrosion starts to become a problem. So we really want to minimize how much water is present in our fuel. The storage stability test is a test done where we take a portion of the fuel and we measure what's known as the color number. So it's a number that's generated, it's defined by the ASTM. This number was originally generated for the brewery industry, so it's shades of brown. And a light number, a low number, so a number of 0 means that this is like water, we can see straight through it. As the number increases in size, the top end of the scale is 8, and 8 would be a stout, a very dark black beer or fuel. So what we do is we measure the number at the start of the test. We then take the fuel and we heat it up for a set amount of time and then check the color after heating. The color, if it increases, tells us that this fuel is darkening and oxidizing due to heat. And the really important thing to look for on the report is a pass-fail. If the fuel is a pass, great, you can keep it in the tank, everything's fine. If it's a fail, we have a problem. And I would suggest speaking to your fuel oil supplier and saying, hey, well, specifically your fuel supplier, this fuel is starting to degrade on us. We need to change it out, and let them come up with a plan as to how they're going to replenish that fuel for you so that you still have fuel that will stay in the tank and still function when we need it to function. All right, that essentially is the key points to cover. I mean, there's a couple of slides here that's talking about very much at the beginning, what are the benefits, what are the things we need to do, and we've got a case study here of a generator where the oil sample identified high metals and dirt being present in the oil. When they investigated, they found that this clamp hadn't been installed correctly, and this allowed dirt to come through this little bottom porch of the hose here, and that's what was damaging the engine and would accelerate wear in the cylinder liner pack area. So running an engine like this in a dirty environment, you're probably looking at about 48 hours and the engine is finished. It will destroy the engine that quickly if you're allowing dirt to get into the engine while it's running. So obviously in this particular case, they were able to identify the problem and take corrective actions and save that engine. Kind of things that we can do for you, but I think we've run out of time, so I'll end the slideshow here and hand over to Kristen to see if we had any questions come up.
Thanks, Gary. It looks like we don't have any questions at this time. So I will go ahead and end our session. And thank you everyone for joining us. We will be having this posted, so you will be able to review all of the information and share this later. If you do have any future questions, just let us know. Reach out to your local lab or to the sales team, and we will go ahead and help you out with that. Thank you, and have a great day, everyone.
Thank you. Thanks for your time. Bye for now.